All right, here we have another example of a discrete time, a stochastic process. Again, time here is really just rounds of the game. What is the game? It's a pretty stupid game, but it's going to help us learn some concepts. Let's say you have a jar here, urn we can call it, and two balls, two ping pong balls, unpainted. We put them in the jar, and then we randomly pick them. So this is the first round of the game. We randomly pick one of them. If it's unpainted, I flip a coin. If it's head, I paint it red. If it's tail, I paint it blue. All right. So red, blue. If it's unpainted. All right. What if it's and then I put it back. Then the next round, second round, starts. So I pick a ball randomly. It could be the unpainted one or it could be the painted one, whichever color it is. If it's unpainted, again, I flip a coin. Head, red, tail, blue. If it is painted, I just paint it the other color. If it's blue, I paint it red. If it's red, I paint it blue. And I put it back. Third round. And I keep doing this. So state of the system is basically a state of this game is how many of each color I have in the jar at a given point or before I start every round of this game. I could have unpainted, red or blue. So a state of the system is a triple. Here I have it. U or B, U is the number of unpainted balls, R is the number of red balls, B is the number of blue balls. So what is X sub 0? Like, how do we start? What is the state of the system in the beginning, basically? In the beginning, we only have two unpainted balls, so that's going to be 2, 0, 0. After the first round, I'm going to still definitely, after I finish the first round, I'm going to still have one unpainted ball because the one that I take out is going to be unpainted. And I flip a coin, could lead to blue, could lead to 0. So it could to red. So it could be either 1, 1, 0 or 1, 0, 1, right? And if at some point a state of the system is 0, 2, 0, which means there are only two red balls in it, what is going to be x sub t plus 1, or what's going to be the composition of the balls in after the next round? Maybe pause the video and think about it. It's pretty simple. It's going to be so the one that I take out is definitely red, right? And the rule of the game is that if it's red, you paint it blue. If it's blue, you paint it red. So it's going to be blue because the one that I take out is red. I painted the other color blue, put it back. So I'm going to end up having 0, 1, 1. One red, one blue. All right. Let's look at another example. Then we'll create the transition probability matrix for the previous one. CSL computer stock. Let's say there is a company CSL with this ticker, and they have a stock. So price of the state of the system here could be the characteristic of the system here could be a stock price, right? And then that price has different states. The states are basically the values, and values change over time. So x sub 0 is the price of the stock in the beginning, and then we have a question. If I know what has been the previous, what has been the price of the stock in the past, let's say in the past 100 days, out of all the records that I have for the stock price in the last 100 days, which one do I need to predict the next price? Let's say it started with $15, then 16, 17, went down, up, now it's 16. Out of these, the only point that I need to calculate, the next one is this, the last one. If that's the case, we call it a Markov chain, where history doesn't really matter. It may not be really the case for a given stock, but at least in this example that we had, for example, at x sub t, I know I have two reds. That's all I need to know to predict the next state, which is going to be red, 0 unpainted, 1 red, 1 blue, right? It doesn't matter how we got there, how we got to two reds. right? The history doesn't matter. So this is a perfect example of a Markov chain. All right. So basically, a Markov chain is a discrete time stochastic process, similar to what we saw in the few examples we saw, and this definition means that this conditional probability. These are two conditional probabilities here. It says at time t plus 1, probability that at time t plus 1 we are in a certain state, say the state of t plus 1, I sub t plus 1. Given that all these states have been assumed in the past, is the same as the conditional probability where you only know the previous state, which is x sub t. All right, basically all of these are useless, right? So you don't need those. If those two conditional probabilities are the same, you could say that it's a Markov chain. So from now on, we're going to show the conditional probability of being at point J, given that in the previous step you were in point I, you were in a state I. We're going to show that with Pij. All right. And note that we have a stationary assumption, which means conditions or rules that are governing the behavior of this system doesn't change. All right, over time. If that's the case, we call it a stationary Markov chain. All right, but the main thing we want to discuss in this video, our main goal is to create this matrix, which is the transition probability matrix. What is it? So this matrix, you read it this way. First, you look at the row, then you look at the column. For example, P22, or let's say P21. The row means that the row is the state you're in now, and the column is the state you're going to next, and P is the probability of that happening. For example, if today is sunny, what's the probability that tomorrow is raining? All right, so that's P13, for example, in the example that we had previously. So here, if you want to interpret this value, this probability, it basically means if today you are in a state 2, because this is the second row, what's the probability that tomorrow you end up in a state 1? 2, 1. Okay? And one rule here is that the sum of all the rows is 1, which basically means you're going to end up in a state in one of them. These probabilities are in each row. These probabilities are basically forming a partition, which means some of them is 1. Yeah. So whenever you want to create a transition probability matrix, all you have to do is to create a matrix S by S, and S is the number of states that you have, and then to get the probability in the matrix, each one of these probabilities, you ask yourself, if I am in this state, state 2, what should happen? So I'm in a state 2 again, or I'm in a state S, whatever. What should happen? Then you calculate the probability of that thing happening, that event. Okay. So, and also we have a vector Q that tells you the probability of starting in a state 1, 2, or S. And some of these is again 1. So here, if I give you this probability, is this transition probability matrix, I ask you how many states are there. Because it's 3 by 3, there are 3 states. And if I ask you what are the unknowns, the question marks, because you want the sum of each row to be 1, basically this is 0.4, this is 0, this is 0, 0. And note that we call this a state where the probability of going from 3 to 3 is 1, which means once you're there, you're going to stay there forever. We call that an absorbing state. It's like Hotel California.